Okay, now that we've finished that first lab, which was a good review of ICND1, we're going to move on into the information, and this is the beginning of ICND2. Now, we're going to start out, interestingly enough, troubleshooting VLAN connectivity. And we start out, I'm going to review what you would have seen in ICND1. Just want to make sure we're all on the same page with this. So we're going to be starting to talk about VLANs. Now, remember that traditionally, in networks, in the early days of networking, okay, we had what they called, or what they referred, we still have what they refer to as a broadcast domain and a collision domain. Now, we have to really start with the definition of those broadcast domain and collision domains to truly understand what the vendors over the last few years have done as far as the multi-layer switches and VLANs and the equipment, okay? So, traditionally, in a layer 2 and a layer 3 environment, we would segment the broadcast domain by putting in a layer 3 device, a router. And before Cisco got into the switching world, that's what we used, was a router that would segment the broadcast domain. Now, in a broadcast domain, as we know from our ICND1 class, all devices will listen to all the broadcasts. In other words, they have to process the packet, and they'll go on an Ethernet network and say, nope, not me, nope, not me, nope, not me, until it gets to the device that we're looking for on an Ethernet segment. This is what's known as a local broadcast. By design, the router is obligated to stop the local broadcast, and traditionally that's what we use to stop the broadcast at layer 3. Now, a collision domain is all of the devices sharing the same bandwidth on the network. Where would we see a collision domain? First of all, a hub was a collision domain, and if it was a 100 megabit full duplex hub with 12 ports, all 12 of those devices would share that same 100 megabit bandwidth. Now, when we move to the switches, every port on a switch becomes its own collision domain. So all 12 of those devices had their own road onto the network. So then they would get a full 100 megabit full duplex road onto the network. So a switch is an individual collision domain on every port. Now, when we actually took the layer 2 devices and the vendors wanted to actually have what they call microsegmentation or true segmentation at a layer 2 device, that's when we came up with VLANs, virtual local area networks. And VLANs will actually then segment both the broadcast and the collision domains on a switch. I've taken that layer 3 functionality and moved it to layer 2. What's typically less expensive? Layer 2 devices, okay? So the industry went with a layer 2 segmentation of broadcast domains, and this is what a VLAN actually is. Now, it's also important before we move on and take a look at our VLAN traffic, because really a good engineer knows about all the traffic that's running on their network. I have broadcast packets which are 255, 255, 255, 255. And all the devices have to pick their head up, listen to the packet, and decide whether it's for them. If not, move it on down the line on an Ethernet segment. I also would have multicast packets. Now, multicast packets are going to be in the range of a class D, which will start with a 224.something.something.something to a 239, right? Because that would be our multicast range class D addresses. Some of these are well-known addresses, and Cisco has many that are registered with the ICNA, and those addresses are used for things like EIGRP, updates, and so forth. Okay, so some of these are used just randomly. We have a random range of numbers, and some of them are assigned, just like our IP addresses. Multicast is better for my network. Why? Because instead of every device having to actually process the packet, only the devices that are pre-programmed to pick up that packet off the network get interrupted. And a good example of that would be CDP, right? Cisco Discovery Protocol uses a multicast packet. And only the Cisco devices will participate with CDP. All right, now a unicast packet would be an IP address designated for one packet, and when we route IP on a Cisco network, we are routing unicast addresses. Okay, we're going to send a packet directly to a device. All right, so important to note, now there's one other type of packet that I don't have up here, which is called a directed broadcast. And a directed broadcast would look something like this. Now, when would I see a directed broadcast on a network? Only when I have a routed network. Because the router is going to take that broadcast address and he's going to yell down the street to everybody on that street using that 172.16.4.255. Now again, you should have covered that in your ICND1. This is called a directed broadcast, and I'm only going to see that type of addressing in a layer 3 network. Because if I didn't have a router, I would not have any of those directed broadcast packets. Now here's something I want to share with you that I think will help you tremendously. I read this in the beginning of time when I first started studying routing and switching. And if you remember these two things, it will help you all the way down the line. Number one, a switch is obligated, now I'm talking about a layer 2 device, a switch is obligated to flood out all of its interfaces except the interface it came in on, all broadcast, multicast, and unknown unicast packets until it learns port to MAC association. One more time because that's so very important. A layer 2 device, which is a switch, is obligated to flood out all of its interfaces, except the interface it came in on, all broadcast, multicast, and unknown unicast, until it learns port to MAC association. That's the job of a switch. That's what makes a switch intelligent. And then after it learns port to MAC association, it will do a filtering, not a flooding, and be more efficient on your network. By the way, something important to note, that switches by default will never learn automatically from a multicast packet. You have to turn on additional protocols for them to learn from multicast. Now, take the situation of a layer 3 device. It has the opposite function. A layer 3 device is obligated to stop all broadcasts at its interface. And that's the segmentation of my broadcast domain. Okay? So understanding that a layer 2 device has a certain job and a layer 3 device has a certain job, you kind of go from there. Okay? All right, so let's take it back to our slide presentation here and let's take a look at VLANs. All right, here's an overview of VLANs, and it's interesting to note that if you ever take a look at the original specification for VLANs, which is back probably early 90s, there was an RFC, a request for comments, that came out that actually stated what the intent of these VLANs were. And I read through that, and the intent of this VLAN implementation is that at every layer of the OSI, I will have an automatic move of an Ethernet device. In other words, at layer 1, physically plug it in. At layer 2, automatically learn the VLAN at layer 2. And this is called dynamic VLAN port association. All of your Cisco Catalyst switches have that ability, it's just nobody ever did it. Most of us just do a manual port association. But we do have the ability and the protocols on the ports to actually go out to a TFTP server and actually query the TFTP server and say, this is my MAC address, what VLAN am I supposed to be in? Okay? And it does have that ability. Now, the only time I've really seen this in the field is now with 802.1x. Okay, 802.1x will actually do a dynamic VLAN association. All right, now VLANs specifically were to enable us to move devices on Ethernet segments without the network engineer getting involved. Like I said, most people, they're going to have to change the port association. Okay, so I always ask my students, on a 12-port switch, if I have access ports, how many actual VLANs can be active on access ports on a 12-port switch? 12, because an access port designates one VLAN. Now, if I have a trunk port, that indicates multiple VLANs. Okay, now my database of VLANs can be as many as the device will support, but if they're access ports, they can have only one active VLAN per port. Notice that in this design right here, we're actually taking these switches and spanning multiple floors in this organization. I've got third, second, and first floor. So how do I actually span the VLANs across multiple floors? I have to send the traffic through a trunk link. The trunk link designates what type of traffic. Is it VLAN 2? Is it VLAN 3? Is it VLAN 4? Because Cisco's implementation of VLANs dictates this. You cannot communicate VLAN to VLAN, broadcast domain to broadcast domain, without routing the traffic first. So somewhere I've got to go to a router or a route processor and take the traffic out, do a layer 3 routing function, and back in again. What designates what packet is destined for VLAN 2, VLAN 3, VLAN 4, the .1Q frame tagging. Now I'm saying .1Q, which is 802.1x. This is Cisco's preferred method of frame tagging. It is an industry standard, and it is now Cisco preferred. Okay, and we're going to be talking in detail about 802.1Q. Like I mentioned before, a good Cisco engineer cannot know enough about 802.1Q and spanning tree, and now rapid spanning tree, which I also will be covering with you as well. Okay, so we've got true segmentation of both the layer 2 collision domain. Everybody has their own road onto the network in a switch. Now, if that was a hub, we'd be in a shared environment. But on a switch, layer 2, I've got my own road onto the network. And then I'm segmenting the broadcast domain, which is the local broadcast, 255, 255, 255, not with a physical device such as a router, but actually in the backplane of the switch. It will segment the broadcast domain. But if I want to communicate, I have to route it out to a layer 3 device. And there you see at the bottom a layer 3 device. By the way, does anybody remember from ICND1, what is the difference between a bridge and a switch? A bridge and a switch are both layer 2 devices. They both do a similar function, but a bridge is a software implementation at layer 2, where a switch is a hardware implementation at layer 2. Now, switches in the old times, the olden days, had like 2 ports and software implementation, and we take 2 Ethernet LANs and extend the Ethernet segment by putting in a switch. You'd be hard-pressed to find one nowadays in the market, okay? Then the vendors came out with switches, and they called them switches just because they thought it would sell more devices. That's the only reason why they really changed the name. But it does have a hardware designation using an architecture called ASIC, Application-Specific Integrated Circuitry. Nothing that they'll test you on, but it's always good to know the architecture that you're working with. Okay, so now in the backplanes of these switches, in other words, in the hardware, ASICs, we're actually going to segment these broadcast domains, and that's what my VLAN actually is. Okay, it's a logical separation. Now, physically, these devices can be on any floor in my network, and I have to go out to a router or a route processor to actually be able to communicate. Notice I keep saying router or route processor, because at layer 3 now, we could have a multi-layer switch that does the routing process in the supervisor card or in the actual hardware. And sometimes it's a physical router, which we refer to as a router on a stick, and sometimes it's a route processor. All right, now if you're going to configure VLANs, you're going to go into your switch, do a config T at the global config, VLAN 2. Do I need to give it a name? Not necessarily. If you don't, it will take on a name of VLAN 0002, placement for 1,000 VLANs. But giving it a name helps us to identify what that VLAN is for. Like you might want to give it a name like accounting or finance or whatever. Okay, and then I'm going to go into the interface and assign that VLAN. This is called static VLAN association.
Start with new learning now.